Welcome, this is IS 4440 Networking and Servers. Today I want to talk about how computers find each other on networks and introduction to servers. So first of all, let's start with our OSI model. And remember, we can remember the OSI model by thinking about the mnemonic device, please do not throw sausage pizza away. So please do not throw sausage pizza away. So the first layer is the physical. Then we have data link. Then network. Then transport. Then session. Then presentation. And then application. At each of these layers, certain rules and certain ways of communicating apply. At the physical layer, we are dealing with on and off signals. And that can come in the form of cable, either electronic or fiber. It can come in the form of RF, radio frequency. This is your Wi-Fi. And also 4G, etc. At the data link layer, the on and off is translated into binary ones and zeros. And the data link layer is also in charge of breaking up these long strings of ones and zeros into manageable chunks called frames. At the network layer, we get what we're going to talk about in more depth today, which is network addressing. At the transport layer, we get end-to-end control, also known as a session. And the session layer is in charge of authenticating sessions from the layer below it. And the presentation layer also takes part in encryption and encoding messages. And the application layer is the one we're probably all familiar with. This is the human computer interface. This is our email client, web browser, etc. So that's the 7-layer model in a nutshell. And if you recall, I said that the 7-layer model for this class, although very important, is less important than the 4-layer TCPIP model. Which takes the 7 layers and compresses them down into 4 layers. And you can remember the TCPIP model with the mnemonic device. Love is the answer. So we have link, internet, or sometimes internet working, transport, and application. Now the same stuff happens in the 4-layer model as in the 7-layer model. It's just that we define each layer a little bit more broadly. So link takes up the physical and the data link parts of the 7-layer model. For example, the internet layer is matched up with the network layer on the 7-layer model. The transport layer is matched up with 3 layers on the 7-layer model, and that is presentation, session, and transport. The application model is one-to-one with the application model of the OSI model. Okay, so let's do this. Layer, function, and our third column, let's do protocol. A protocol is a language. Each layer has different languages that it uses to communicate with the other layers. These are protocols. And I'll make a grid so it's a little bit easier to see. The protocols at layer 1 are things like Ethernet, USB, 802.11, which is Wi-Fi. The protocols at the network layer include IP, Internet Protocol, ARP, Address Resolution Protocol, and others. The protocols at the transport layer mostly revolve around TCP, Transmission Control Protocol, and also its counterpart UDP, User Datagram Protocol. At the application layer, we have a lot of protocols, but some of the most important to remember are HTTP, Hypertext Transfer Protocol, SMTP, Simple Mail Transfer Protocol, DNS, Domain Name System, DHCP, etc. Moving past the TCPIP model and looking at each layer a little bit more in depth, at the link layer, we need to understand that things happen in binary. Binary is the language, the number system that computers ultimately use to talk to their internal components as well as to components that are communicating with them over a network. Binary only has 2 values, 1 and 0. Humans are more familiar with base 10. This binary is base 2. Decimal is base 10. And we have more options for numbers. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can create all of our numbers from those 10 digits. There's another base of number systems that you will find as you go further into IS, and that is hex or hexadecimal, which is base 16. And that includes 0 through 9 and A through F. You'll use hexadecimal a lot if you go into web design, because a lot of colors in web design are indicated by their hexadecimal values. So for example, you would see $000 F1A, and that would be a particular color. Although I don't know which color that is, I just came up with it randomly. So can we convert between these 3 number systems? The answer is yes, absolutely. Remember that binary is ultimately what a computer uses. No matter what number system is given to it, it has to convert everything to binary. So how do we convert, for example, base 10 to binary? Converting base 16 to binary is a little bit more difficult, a little bit more time intensive, so let's worry about converting base 10 to binary for right now. Given a binary number, let's just do a 4-digit binary number, 1010. How do we translate that into base 10? In other words, what number is that binary value? To do that, I find it's easiest to make a little chart that has boxes for the number of digits you have, in this case 4, and we need boxes on top and boxes below. And on top, we write out the powers of 2, starting with 2 to the 0, which is 1, 2 to the 1, which is 2, 2 to the 2, which is 4, 2 to the 3, which is 8. Do you see how this is really converting a base 2 number system into a base 10 number system? The powers we raised are really just counting up from 0 in our base 10 number system. Now, we start at the right side and we input our binary value, 0, 1, 0, 1. Now this part is easy. We simply bring down all of the base 10 digits that are turned on. Remember that 1 indicates on, 0 indicates off. So we bring down a 2 and an 8. Remember, 4 and 1, those are off. And we simply add them together to make 10. So 1, 0, 1, 0 in binary is 10. Kind of cool, right? And that leads me directly into network addressing because it's important to understand binary and hexadecimal when we talk about network addressing. In other words, how do computers find each other on a network? For this class, I want to talk about 2 types of network addressing. We have MAC and IP. We'll go more into depth with IP, but a MAC address is a hexadecimal value It is usually hard-coded into a piece of hardware by the manufacturer. And I should say that MAC stands for Media Access Control. MAC addresses can be spoofed, meaning that hackers can hijack MAC addresses to impersonate a legitimate device on a network. We'll talk about that more when we talk about security. MAC addresses are 6 bytes long. Which is 48 bits in hexadecimal. So it'll often look like something, I'm just going to come up with a random MAC address, 01, A4, C2, 12, 63, E6. And the first part of this MAC address is called the OUI, the Organizationally Unique Identifier, which indicates the vendor. And the second part is the device ID. So what you'll often find on MAC addresses is devices that all come from the same vendor might have this first part of the MAC address exactly the same, and the second part of the MAC address will be unique to that device. You can find the MAC address usually on a sticker or some sort of etching on the actual hardware device, or you can do an IP config /all, and it will show you MAC addresses of your devices. And I'll go through that in just a moment. MAC addresses, still on Mac, only exist on the network segment. That means that once a device sends stuff out to the internet or to another network, the MAC address is stripped from the datagram. It's stripped from the information that it sends. Let's draw a simple diagram. This is you. This is coworker in a different facility. Let's say across the country or something like that. You're sending an email to your coworker, and to do that, it has to go through your corporate network. Then the internet, then down to your coworker's corporate network, and finally to your coworker's computer. Well, the MAC address is only going to exist here, and depending on how your corporate network is set up, it may exist here, but this router at the edge of the internet and your corporate network is going to strip the MAC address. MAC addresses are not allowed on the internet. To draw that in more detail, let's say this is you, and this is your coworker, and it looks like this. Switch, R for router, switch, Wi-Fi to your coworker's computer, and you're sending a message this way, okay? Switches pass MAC addresses. Switches exist on the same segment, but once you hit a router, it's a new network segment or a new network. MAC address stops there, so MAC address stops there. The only address that is consistent across the whole communication is an IP address. And I'll show you how to find your IP address in just a moment. But let's talk about IP addresses. An IP address is a binary value. It is 32 bits. So 32 ones and zeros. When we look at an IP address, it's often converted to base 10 so we can understand it. And it's in this format: 3 numbers, dot, 3 numbers, dot, 3 numbers, dot, 3 numbers. And these are octets. And they go from 1 to 255. Although 255 is a reserved number, as we'll see. And again, total of 32 bits. And I should say we're talking about version 4 here, which is still the most widely used IP address version. So an IP address at your home might look like this: 192.168.004.001. Sometimes the zeros are not there. To your computer, though, that number is actually in binary. So it's 11.00000.101010000.000000100. .0000001. Now we know how to convert these back and forth now, don't we? We use our chart. We just use a longer chart. So you can convert 11000000 back to 192 using that chart. A 32-bit total value has a maximum mathematical amount of IP addresses of something like 4.2 billion. Recall that everything that communicates on a network in the modern world has to have a unique IP address. There are about 7 billion people on Earth. And even if we said that only half of them have access to the internet, you're still looking at 3.5 billion devices or people that need IP addresses, and each person has at least 2 devices, right? You have a cell phone and a laptop, or a cell phone, an iPad, and a laptop. So you're back up to 7 billion, but we only have 4.2 available. So how does this work? The first way it works, and the most ubiquitous way it works, is that we have 2 types of IP addresses, public and private. Public IP addresses can traverse the internet. Private IP address exists only internally. Taking the example of your home, Xfinity or Google Fiber or whatever provider you have gives you a public, gives you one public unless you buy more. Going into the router that they give you, it translates it into basically 65,000 private IPs. So that's how you can have a party with all of your friends, and all of them are connected to your wireless network. They're all going out through one public IP address that you lease from the carrier as part of your monthly fee. This translation is called network address translation, or NAT, and it's how most homes are getting out on the internet in today's world. If you look at your IP address from your home, it will probably, as I said, start with 192, 172.16, or 10. Now, these 2 are more common in the corporate world. I would say most corporations purchase a block. You'd think a college teacher would know how to spell, of public IPs. They NAT those IPs and give internal employees private IPs. And remember, private IPs start with one of these 3 numbers. Now, it seems that this isn't really a way to mitigate this 4.2 billion stopping point, this 4.2 billion maximum. The other way is IP version 6. And IP version 6 has been slowly taking off for about a decade now, but there are lots of costs for businesses involved in switching over to IP version 6. So most of them are still sticking with IP version 4 because it still works and it makes sense financially. But an IP version 6 is a hex value, and if we take a look at the anatomy of an IP version 6 address, let's just say it's something like we might have something like this section has a routing prefix, this as a subnet ID, and this as the interface. In other words, this is the network interface for your device. This is the subnetwork you're on, and this tells it how to get where it's going. But as you can see, this is a much larger value than a 32-bit IPv4 address. It is 128 bits long, as opposed to the 32-bit IPv4. Now remember, this number is exponentially larger than this number. So how many IPv6 addresses are there? In theory, 2 to the 128, which is also known as 340 undecillion, or a 1 followed by 38 zeros. Can we write that out? There we go. Well, actually, this would be 340. Yeah, there we go. And that compares, so that's version 6. Version 4, remember, has roughly 4, that many. So we have a huge difference in the number of IPs. As one network engineer puts it, we could assign an IPv6 address to every atom on the surface of the Earth and still have enough addresses left to do another 100 Earths. That's an astronomical, pun intended, number. I think we'll find a way to use it. Remember in the 60s when IPv4 was coming out, there were 12 computers in the whole world. They said, we'll never use 4 billion, that's impossible. I think we'll find a way to use 340 undecillion addresses. Okay, moving on from IP addresses. Once the data actually gets to the destination, so let's say the destination is it also needs to know how to get in the house. Think of the IP address as the street address, and then you would have colon and then the port number. So IP port. The port is the door or the window through which data enters and exits the house, the device. Notice I put 80 here. Port 80 is the most used port. Port 80 is for internet traffic. And there are other well-known ports that we need to know about. So let's divide the ports here. We have well-known, 80 internet, HTTP, web traffic, right? 443, secure, HTTP. 25, SMTP, simple mail transfer protocol. When you send mail, unless it's encrypted, it goes out on port 25. And 21, FTP, that's file transfer protocol. '53 is DNS, which is domain name service that translates an IP address into a website name, like google.com. And those are pretty much all we need to know for this class. Port numbers go from 0 to 65535. And they're split up like this. 0 through 1023 are privileged. And of course including the well-known ports that are reserved for certain applications. And 1024 through 65535 are ephemeral. Or we can also say they're temporary. If an application needs to grab a port to use for a temporary reason, it grabs one from 1024 to 65535. So for example, if you have a specific application that is not using one of the well-known ports, like an application from a specific vendor, it may grab an ephemeral port to send and receive data temporarily each time it sends and receives data. On our TCPIP stack, ports exist here at the transport layer. The ports are a transport layer function. When we bring up the ipconfig window, and we can do that here by clicking Start, typing in CMD, and if you right-click on it and choose Run as Administrator, you'll have a lot more privileges to look around. And here's mine. For this demonstration, though, I'm going to use a fake window that I have here. And let's take a look at a few things that we can tell just by doing this ipconfig. We have our IP version 6 address, and we've been assigned 2. Right there. Actually 3, there's a link local IP version 6. We have a DNS name right there. We have our IP version 4 address and subnet mask. And if you can see there, we also have, it looks like an IP version 6 subnet mask as well. And then we have the default gateway. And that's just doing the ipconfig command. If we do an ipconfig/all, we can see a lot more information, and I'll show you that now. Now we see a lot more information about my connection. For example, my machine has multiple adapters. We have a wireless LAN adapter here that's disconnected. We have another one that's disconnected. We have a Bluetooth adapter that's disconnected. We have a tunnel adapter, that's for my VPN, that's disconnected. And we have some information about my corporate network, including DNSs. We have 2 other Ethernet adapters, so these are just the plug-in network cards, network adapters. One's disconnected, one is connected. This is the one I'm connected with now. Here's the domain I'm on. Here's the name of the adapter. Here's the MAC address, starts with C4. We have DHCP enabled, which means it's asking for an IP address from the server. We have a IP version 6 address and a version 4 address. We have DHCP information, meaning how long do I have this IP address for. We have default gateway, server information, and a bunch of other information. So that's an ipconfig for you. Okay, and this concludes our networking segment. Next video will be our Introduction to Servers segment. Thank you.